All right, so now we're going to have a series of quick teaser talks. These are sort of 1 minute, 1 slide talks from each of the demos, which are located all the way at the other end of this building. So walk out this door and go all the way down and then turn to the right. There's a demo room there. So if Yibo is here and could come up. Okay, so the first demo talk is on high-fidelity validation of P4 networks with Sonic P4 software switch and CrystalNet, and Yibo will give the talk.
All right, thanks for the introduction. Good morning. So we, today from Microsoft, will show you a large-scale emulated P4 networks. It has more than 500 P4 switches connected in the real Microsoft data center topology. So we do this because we want to test or validate our innovations in the network. Say the innovation can be in the data plane, like P4-based new features, or the innovation could be in the control plane. We integrate Sonic with P4. Sonic is an open source switch OS that runs the exactly same code in Microsoft data centers today. Also, with CrystalNet or management plane, you can test any topology or real configs, route announcements in the network. So for the demo, we use all the real ones from the production. So find us at the demo place. So this probably will be the largest P4 network you have ever seen and the most realistic one. Okay, so our talk will show more details at 11:15 in the morning. Thanks.
Okay, so the second talk is on a P4 to Wireshark dissector, and Ruris will give the talk.
Hi, I'm Yorgos from Barefoot Networks. So one of the most powerful features of P4 is the ability to define new protocols. And of course, new protocol definitions come with new packet header definitions. Now, at some point when we're trying to work around a new protocol, we're destined to collect a trace using TCP dump, and we're usually going to go ahead and analyze that using a tool like Wireshark. Of course, Wireshark does not really know about anything about our new protocol, and this is where our program comes in. So it takes as input a P4 program, goes through your header definitions, and creates Lua dissectors for Wireshark, which you can load and get a nice visual representation of your packet and see what's going on with the different fields in your packet header. Thanks.
Okay, so the third demo talk is on future P4 use in SAI. Jonathan.
That's not Okay, so Jonathan from Mellanox, and I'm going to talk about a SAI software switch using P4. Okay, so SAI, if you don't know, is a switch abstraction interface, stands for switch abstraction interface, and defines the API to provide a generic vendor-independent way of controlling any forwarding elements. It's supported by many of the leading vendors and the ecosystems like we just saw, Sonic. What we're really saying is that SAI, the most important, why, okay, let me restart. So why do we need a software switch for SAI, and why P4 is the best tool for the job in our opinion? We want to provide a conformance test. What we're saying is that API alone is not enough. You really need to define the way that the behavioral model of your switch, and we want to really define compliance, you really need to define a specific model. The use of it is to port application and port on top of the hardware agnostic models. And just a second about the future reference of it, future use outside of the software switch of P4 inside is to enable some flexibility. So the roadmap, and I'm out of time, so I'll finish now.
So come to the demo booth to hear the rest of that sentence. Okay, so the next lightning talk is by Amado Sapio. He's going to tell us about DAIET, data aggregation in the network.
So, good morning. I'm Amado Sapio from KAUST, and I'm here to present DAIET. That means data aggregation in network. And the goal of this project is to perform data aggregation along network paths using programmable network devices. This helps the work of big data and machine learning applications. Specifically, DAIET tries to offload to switches and smart NICs some of the computational tasks performed by those applications, so that we can reduce the amount of traffic and also reduce the amount of work done by those workers. So if you want more details, please stop by my desk, and thank you for your attention.
So next up, Srinivas from MIT will tell us about hardware software co-design for network monitoring.
Thank you, Nate. The title of the talk isn't on the slide. So yeah, the title of the demo is Language-Directed Hardware Design for Network Performance Monitoring. So here I'll be walking you through our proposal for a model of network performance monitoring. So in some sense, we have a performance query language that allows network operators to have a network-wide view and write fine-grained performance monitoring questions, which are then compiled by our compiler into switch programs in P4. And we use the behavioral model to actually show how this kind of debugging might actually work. So as a concrete example, I'll be walking you through an example where we debug this problem of high tail latencies, where you have two traffic sources that are contending at a single queue, where one of them is a bursty UDP source and another one is a TCP RPC that's downloading a small-sized object. And I'll be walking you through how an operator can localize where the queues are building up, figure out how the queues are actually building up in some sense. Is it bursty, or is it because a lot of multiple flows are actually contending at the same queue? And we'll be able to figure out which traffic actually caused the queue buildup. Okay, thanks.
All right, last but not least, Stephen Ibanez from Stanford will tell us about P4 Net FPGA.
So the P4 Net FPGA project is a joint collaboration between Stanford and Xilinx and Cambridge University. And it's something that we put together to try to make it easy for P4 developers who might be unfamiliar with hardware description languages to run their P4 programs on the Net FPGA platform. The Net FPGA platform, for those of you that don't know, is an open source, line rate, FPGA-based platform specifically designed for the teaching and research communities. So the P4 Net FPGA flow uses the Xilinx P416 P4 SDNet compiler to compile those P416 programs into HDL, and it supports the extern functionality defined in the P416 language specification. And what we've done is create a library of extern functions that implement the domino atoms, which were proposed at SIGCOMM of last year. And these atoms can be instantiated in P4 programs and then used to perform atomic operations on state stored in the switch. And so for the demo today, I'll show you how we can compose these atoms to implement to write a switch design that monitors TCP/IP flows to compute the flow size distribution directly in the data plane, and then the control plane can read this flow size distribution off of the switch and display it in real time. So come by the demo to check it out.
All right, so that concludes the first session. We have a nice, healthy break, so please step outside, get some sunshine, get some coffee, and then come back inside and go see the demos at the end of the hallway. And we'll come back at 10:55.